nitrogen cannot be used directly from the atmosphere. It needs to be converted and fixed into nitrogen compounds through a natural atmospheric phenomenon called the nitrogen cycle. Nitrate is an essential element as a nutrient for growth and metabolism in the plant. It can be found in the soil, food such as in vegetable as well as in water bodies. As the world population growth is accelerating over the years, this increases the pressure on energy and food production. To achieve that, the application of nitrogenous fertilizer is one of the solutions to complete the demand for food security. However, synthetic fertilizers are harmful and toxic. When it comes to groundwater analysis, nitrate is the main contributor to water pollution. Other than fertilizer, landfill leakage, animal manure, and urban sewage leakage is also anthropogenic sources of nitrate. The concentration of nitrate for both non-agricultural rural and urban areas can be as high as agricultural land fields, and it is transported to the water bodies from terrestrial by process of surface runoff and leaching from the soil. When nitrate ions enter the source of potable water, it can be a serious threat to human health. For instance, public water supplies containing nitrate can cause ovarian and bladder cancer. Toxicity also leads to methemoglobinemia or blue baby syndrome under 1 year old. Rich nitrate in the water becomes favorable conditions for the growth of aquatic plants, algae, and microorganisms. This will create slime layers on the top of the water surface, promoting eutrophication. Water with a mass volume of algae and anaerobic organisms will form a thick layer of green scum, make water turns cloudy, and release harmful gases and a foul smell. The decay of dead plants and algae produces algae toxins and promotes the wide spread of disease and thus will deteriorate water quality. Since nitrate is colorless and completely soluble in water, methods such as membrane filtration and conventional water treatment are unable to remove nitrate from water. The adsorption technique is proposed to overcome the limitations of conventional practice. To achieve this, we invented an advanced polymeric adsorbent to remove nitrate ions from water. We fabricated a new adsorbent material called surfaced ion-imprinted polymer on modified graphite for the removal of nitrate in the fixed bed column. This research was successfully done by fellow members of the Faculty of Chemical Engineering and Technology UNIMAP. Now, without further ado, let me show you the reliability of this method. Ion-imprinted polymer is an advanced polymeric adsorbent with tailor-made receptors as it can selectively recognize and bind with target ions. The polymerization start with the functional monomer and template ions are mixed together to allow self-assembly by covalent or non-covalent interaction in the solvent, followed by the addition of initiator to initiate the polymerization reaction between monomer template complexes with crosslinker. Then, the template will be removed from the polymer matrix, leaving the active sites that complementary to the shape, size, and arrangement of the template ions. In this project, the graphite ion-imprinted polymer, GIIP, was synthesized by precipitation polymerization using surface imprinting technique. The graphite was modified with silane coupling agent 3-methacryloxylpyl trimethoxylane to introduce the vinyl groups on the graphite sheets. The monomer and template ions were dissolved in the solvent to facilitate the self-assembly between the monomer and the template. Then, the modified graphite was added to allow the monomer template complex to bind with the graphite surface, followed by adding a crosslinker and initiator. After 18 hours of polymerization reaction, the polymer was washed 3 times with methanol and double distilled water to remove unreacted chemicals. And lastly, template ions were removed from the imprinted polymer using 1 molar HCl methanol until there is no trace of nitrate ions. And the GIIP was further applied to remove nitrate ions from water using fixed bed column. The fixed bed column was utilized to analyze the dynamic adsorption of nitrate ions in aqueous solution. The column was packed with 0.1 to 0.3 gram of GIIP with particle size of less than or equal to 38 micrometers to obtain the bed height of adsorbent that equivalent to 0.6 to 1.7 centimeters, respectively. The inlet solution within 200 to 1000 ppm was pumped into the column from bottom to the top with flow rate between 1 to 3.0 milliliters per minute at room temperature. The effluence was collected at predetermined time intervals and the nitrate concentration was tested using UV-vis spectrophotometer at the wavelength of 301 nanometers. The morphology and characteristic studies were analyzed using SEM and TGA analysis. The SEM analysis shows the graphite exhibited dense and smooth surface. The surface morphology of GIIP and GNIP changed significantly after polymerization of monomer and crosslinker. In comparison to graphite, both polymers had rough and uneven surfaces. GIIP was more porous and bulky compared to GNIP due to the presence of cavities in the GIIP matrix. The TGA was performed in the temperature range of 37 to 600 degrees Celsius. The key decomposition events of GIIP and GNIP described based on the two phases of significant weight loss. The first phase of decomposition at temperature below 100 degrees Celsius, due to elimination of water between polymer layers. The second phases discovered at temperature range 300 to 450 degrees C, due to the degradation of crosslinker in the polymer matrices. The total mass loss of GIIP and GNIP was estimated to be 70.21% and 69.82%, respectively. However, there was no significant loss of weight in graphite and modified graphite, GMPS. This indicated that polymer was successfully coated on the surface of modified graphite. The performance of GIIP was evaluated based on three parameters. Firstly, influence of flow rates. The effect of flow rate on the adsorption of nitrate using GIIP was evaluated by varying the flow rates 1 to 3 ml per min while the others kept constant. The breakthrough time and exhaustion time of the GIIP occurred faster when the flow rates increased from 1 to 3 ml per minute. The breakthrough and exhaustion time decreased for the increase in flow rate from 1 to 3 ml per minute. The highest percentage removal of nitrate ions was 77.37% at 1 ml per minute. At low flow rate, nitrate had more contact time with adsorbent, which higher nitrate removal in column. Second, the effect of bed depth was evaluated by varying the bed height from 0.6 to 1.7 centimeters. The breakthrough time and exhaustion time increased when bed height increases. The percentage removal of nitrate increased to 81.27% at 1.7 centimeters, higher nitrate uptake at the highest bed height, more binding sites available for adsorption. The effect of initial nitrate concentration, 200, 600, and 1000 mg per liter, was studied on the breakthrough curves. From the graph, the breakthrough time decreased as the concentration increased, due to more adsorption sites filled with nitrate ions at shorter times. The adsorption of nitrate ions on GIIP and GNIP was conducted with the initial concentration of 600 mg per liter, flow rate of 1 ml per minute and bed height of 1.7 centimeters. When comparing GIIP with GNIP, the adsorption capacity of GIIP was higher than GNIP. This was attributed to the cavity sites that were complementary to the geometry of nitrate ions. Adsorbent was evaluated by regenerating GIIP in a fixed bed column. The saturated column was regenerated by 1 molar methanol/HCl and pumped into the column at flow rate 1 ml per minute until all the adsorbed nitrate ions was extracted from the adsorbent. After 4 regeneration cycle, the percentage removal of nitrate ions relatively high, 75.26%, with adsorption capacity 84.924 mg per g. The performance of GIIP was further assessed using real water sample, operated at flow rate 1 ml per minute and bed height 1.7 centimeters. The breakthrough and exhaustion time for GIIP were 43.52 minutes and 68.72 minutes, respectively. The removal efficiency towards nitrate ion for GIIP, 82.61%, higher than GNIP, 73.15%. This results implies that GIIP can be considered a reliable method to remove nitrate from water. Furthermore, the cost is effective and green procedure. Compared to the other adsorbent in the market, the cost production of GIIP much more cheaper. In conclusion, this method is first ever attempt to use precipitation polymerization by surface imprinting technique to prepare modified graphite IIP and implemented in fixed bed column for removal of nitrate ion. Moreover, the GIIP has potential application to use in agricultural field, wastewater, food and pharmaceutical treatment. It also can be further applied as sensing materials to detect nitrate in water. That's all from us, thank you, and have a nice day.